We now address the issue of static determinacy versus static indeterminacy. We will also look at two special cases of statically determinate members, two-force and three-force members. Not all combinations of restraints may adequately support a body. In two dimensions, there are three possible rigid body motions: translation in two planar directions and rotation about an axis perpendicular to that plane. This suggests that if we have three restraints, that should be sufficient to prevent these motions. What we will see in this section is that having three restraints is a necessary but insufficient condition to ensure the two-dimensional body is restrained. It is also necessary to have an appropriate arrangement in addition to an appropriate number of supports. If the combination of number and location of restraints is sufficient, we say that the structure is fully supported or that it has complete fixity. As an aside, the word fixity seems like an abomination of the English language, but nevertheless we will continue to use the term. If the body is not fully restrained, we say that it has partial fixity. If you go back to one of our earlier examples in Chapter 3, we had an engine that was being lifted by a winch. In the vertical direction, the engine is supported. In the horizontal direction, there was neither a force nor support, and force equilibrium in the horizontal direction produced the trivial equation 0 equals 0. I said at the time this indicated an ability to undergo rigid body motion in that direction, and it is easy for us to imagine the engine swinging very slightly back and forth in the horizontal direction as it is being lifted. In this case, the engine's level of support is one of partial fixity. If the body in question is a structure consisting of an assembly of individual members, and partial fixity implies that one member can experience translation and/or rotation relative to the other members, the body is said to be a mechanism. Three or more supports of appropriate configuration are required to maintain equilibrium of a body in two dimensions, and six or more supports of appropriate configuration are required to maintain equilibrium of a body in three dimensions. If the body has more than 3 or 6 supports, additional information beyond the constraints provided by the equilibrium equations are required to solve for the support reactions, and we say that the body is statically indeterminate. If the body has fewer than 3 or 6 supports, it likely has the ability to exhibit rigid body motion. This means that the body can translate or rotate without violating the support reactions imposed on it. We will be able to see what this looks like in the examples that follow. A rule of thumb to determine if a body is statically determinate or statically indeterminate in two dimensions is to compare the number of equilibrium equations, which is 3, to the number of unknown reactions, we'll call it n. An unknown reaction component exists for every degree of freedom, translation or rotation, impeded or prevented by the support. If n is less than 3, the body is statically determinate and it can have partial or no fixity. We should mention a body with no fixity is completely unsupported, and we are unlikely to encounter any such example in statics. The difference, 3 minus n, often tells us the number of rigid body motions the body is capable of exhibiting. If we really had no fixity, then the body would be able to move in any way it likes in two dimensions with some arbitrary combination of translations and rotation. Let's go back to our example of the engine block being lifted vertically. If we are treating this object as a particle, then there are only two equilibrium equations, force equilibrium in x and y. There is a single support in the form of a cable or chain used to hoist the engine. The fact that n equals 1, which is less than 2, indicates partial fixity, and we look for a single rigid body motion. We observe that the engine can swing gently back and forth in the horizontal direction without violating its supports. If we are treating the same engine as a body, then there are three equilibrium equations, and n equals 1 is less than 3 indicates partial fixity with 3 minus 1 or 2 rigid body motions. As a body, the engine block is both capable of experiencing gentle rotations in the out-of-plane direction in addition to swinging back and forth in the horizontal direction. If n is equal to 3 and the supports are properly configured to ensure complete or full fixity, then the body is statically determinate. If n equals 3 but the supports are not properly configured, the body has partial fixity and is statically indeterminate. Finally, if n is greater than 3, the body is statically indeterminate. It may have complete or partial fixity, again depending on the configuration of its supports. It is easier to appreciate the distinctions between these different cases by looking at some examples. Here we have an example of the same body supported in 10 different ways. It may be helpful to add an external force, a weight say, to see the different conditions. In the top row, we have three cases that correspond to n equals 3 with complete fixity and therefore represent statically determinate cases. It may be easier to see the n equals 3 than the complete fixity, so let's take some time to look at these cases individually. I will call the left and right side supports A and B respectively, so I can give some consistent labels to the support reactions. In part A, we have a roller support at A and a pin support at B. Remember that the roller support is just a shorthand for a lack of resistance parallel to the roller plane. So there is one support reaction here in the normal or Y direction. The pin support at B indicates translation is prevented in both X and Y directions, so there are two reaction supports here. This gives us a total of n equals 3. How do we know there is complete fixity? There are two approaches to this. One is to try to imagine the body undergoing translations and rotations without violating its constraints. The structure can't translate as a rigid body without violating the pin support reactions at B. If the roller were literally a roller, let's say a single ball bearing on which the left side of the structure were resting at A, then there would be no ability of the roller to pull down on the left side of the structure, and we could experience a rigid body rotation about the pin support at B without violating the support at A. But the roller icon is not meant to be literal. Unless stated otherwise, it is as capable of exerting a downward force as an upward force, and under these circumstances, no rigid body rotation is possible. The second way of confirming fixity is to write the equilibrium equations for the body. If one of our equations ends up being 0 equals 0, that is a signature for a rigid body motion in the degree of freedom corresponding to that equation. In the present case, writing the force component equations and one moment equation for this structure will produce no instances of 0 equals 0, and the structure has full fixity. In part B, we have a structure that is built in or clamped at B. The support prevents all motions, so there are three support reactions at B, two force component reactions and one moment reaction. No rigid body motion is possible without violating the supports at B, and none of the equilibrium equations yield 0 equals 0. In part C, we have something more subtle. We have a pin support at A, and what appears to be a cable length at B. We have two force component reactions at A, and one force component at B directed along the geometry of the cable. But whether this force component exists depends on the nature of the forces loading the body. If the force is due to the body's weight, as presently shown here, then the cable will be in tension, n will be equal to 3, and the body has complete fixity. If for some reason the force loading the body comes from below, this force induces a compression at B. But if the support is a cable, it can't support compression and the cable goes slack. Now the number of reaction components is reduced by 1 to just the two force components at A, and we can imagine the structure experiencing a rigid body rotation counterclockwise about A. Cases D and E represent support configurations that are statically determinate with partial fixity. In both cases, the force reactions at A and B are purely vertical, and the horizontal force component equation produces 0 equals 0. Both situations permit rigid body translation in the x direction without violating the body's constraints. The combination of vertical force equilibrium and moment equilibrium permits us to find the reactions at A and B, making it statically determinate in spite of its partial fixity. Case E is not quite as unrestrained as case D, because as the body translates in x, the orientation of the cable at B changes. With finite displacement, the cable develops a force component in the horizontal direction, inhibiting the range of motion the body undergoes in x. It is still statically determinate with partial fixity, just with more limited range of motion than in case D. Also, just as in case C, this is predicated on the cable being in tension. If the force applied is from below and the cable goes slack, N is reduced to 1 and the body can undergo both rigid body translation in x as well as rotation about the roller support at A. Cases F, G, and H all represent statically indeterminate support configurations. In case F, we have one vertical force component reaction at each of the two rollers and two force component reactions at the pin. In case G, we have a roller support at A and a built-in or clamped support at B. Both F and G have complete fixity. Case H is statically indeterminate, but with four roller supports providing force reactions in the vertical direction, the structure is free to move in the x direction without violating those restraints. In this case, it is both statically indeterminate and has partial fixity. The last two cases, I and J, represent cases where n is equal to 3, but the lack of appropriate support configuration results in partial fixity. In fact, case I looks a lot like case H, just with one less support. This body is again capable of rigid body translation in X. The last case, J, is a bit more tricky. We have a pin support at A and a cable support at B. In fact, this looks almost identical to the statically determinate case of C, but with a different cable orientation at B. What's different about this case? Note that the lines of action of all the force reaction components intersect at A. If the body is loaded by its own weight, with a moment arm, let's say of L, from A to the weight, then the moment equation about A results in minus ml equals 0. It is never a good sign when an equilibrium equation has a non-zero quantity on the left side that must equal 0 on the right side. In this case, equilibrium is only possible if the body experiences a finite clockwise rotation about A that changes the cable orientation enough at B so that its line of action no longer goes through A and it is capable of exerting a restoring moment at A to balance that of the weight. In effect, case J morphs into case C, but only after undergoing a finite rotation about A. These 5 movies provide a visual description of the rigid body motions possible in the 5 cases where partial fixity is present. Let's take a look at an example that provides 6 bodies supported in different ways. To make things simpler, I'll assume each body is loaded by a force from above. This way we don't have to concern ourselves with 2 possibilities for cases B and E, one where the cable is in tension and one where it is going slack. In case A, we have a roller support at left, which gives us 1 reaction component, and a pin support on the right, which gives us 2, so we have a total of 3 reaction components. The configuration is sufficient to prevent rigid body motion, so we're going to say that this has full fixity. We'll use F for full and P for partial. N is equal to 3, and the structure is statically determinate. In case B, we have a vertically oriented cable at the left, which provides a vertical reaction, and one roller support on the right, which provides another vertical reaction. There are two reactions. They're both vertical, so we only have partial fixity. We can translate back and forth in x without violating these constraints. So we have partial fixity, but we can determine the loads from vertical force and moment equilibrium on that cable and roller respectively, so this still is statically determinate. In case C, we have a built-in support at left, which gives us 3 reaction components, a roller at right, which gives us an additional 1, so we've got 4 reactions. The body is fully restrained. It can't move. It has full fixity. It's statically indeterminate because we've got one more reaction than we have static equilibrium equations. In case D, we're simply built in at the right. That's going to give us 3 reactions. We have full fixity, and that will be statically determinate. In case E, the cable will give us 1 reaction, the roller 1, and the pin 2, so we will have 4 reactions. We have full fixity, and this is statically indeterminate, again because we have one more reaction than static equilibrium equations. And finally, in case F, we have 3 vertical force reactions, but they are not of sufficient configuration to prevent rigid body translation in X. So this has partial fixity, and because we have these 3 roller supports, vertical force equilibrium and moment equilibrium together will not be sufficient to determine how the force is distributed between those 3 rollers, so this is still statically indeterminate. These results are summarized here. As a second example, we have a model for the suspension of one wheel of an automobile. The coil spring shown in green is going to be a shock absorber. What's not shown there is that it's going to be attached to the automobile chassis, and while that isn't represented in the 3-dimensional perspective view, it is effectively represented here. The wheel assembly is also attached to a torsion bar, and in the same way that a cylindrical bar can exhibit linear spring-like behavior, as we discussed in Chapter 3, it can also exhibit torsional behavior, torsional spring behavior, so it doesn't actually, again, have to look like a coiled element in order to exhibit that behavior. And this is represented schematically by this torsional spring constant here. Just as we were able to show in Chapter 3 that for this kind of an element, we could write the spring constant as a product of cross-sectional area, elastic modulus, and divided by length. We can use the geometry and material properties to come up with a similar torsional spring constant for such a torsional bar. For the idealized 2-dimensional model shown at lower right, we'd like to use our equations of static equilibrium to establish a relationship between the load P applied at the tire and the deflection delta C at that location. So our attention is going to be focused on this red element, which is a simple 2-dimensional model of this lower control arm. And so we're going to be isolating this like this, and our corresponding free body diagram will look like this. So at A, we're going to have pin reactions AX and AY, and then the torsional spring is going to give us a restoring moment. So when the tire tries to move up, that is going to be compensated by a restoring moment that goes in the opposite direction. So if delta C is going up, that corresponds to an initial attempt to experience counterclockwise rotation for the control arm, and that is met with a restoring torsional clockwise moment that goes in the other direction. So we're going to write this as the torsional spring constant times angular displacement. For the restoring force provided by the shock absorber, we're going to have a spring force, which we're going to write as a spring constant K times the deflection at B. And then finally, we've got the load applied to the tire out here at P. And this deflection we're calling delta C. We want the relationship between P and delta C. Now, what's going to make this possible, we're assuming small displacements, and we're going to treat this lower control arm as rigid. So if we were looking at the deflected shape of this, it would end up just essentially being a straight line, and that's going to give us a relationship between the deflection at B and the deflection at C, and also the rotation theta in delta C. So this dashed line is essentially showing us that we can treat the relative deflections as similar triangles, and the vertical deflection at B would just scale with the vertical deflection at C by 4 over 4 plus 5, or 4 over 9 times the deflection at C. Also, for small angular displacements, the rotation theta would just be delta C over the length of that control arm, which is delta C over 9 inches. Now we can get the relationship that we're seeking by just taking the sum of the moments about A and setting that equal to 0. And here we've got first a counterclockwise or positive contribution from the force applied on the tire, P, through a distance of 9 inches. We have a clockwise contribution from the shock absorber, which is the spring force times the distance between B and A, which is 4 inches. And then we have the restoring moment from the torsional spring, which is the torsional spring constant times theta is equal to 0. So now we can rearrange this. We can write P is equal to the spring force, which is the spring constant K, times the deflection at B, which is 4 over 9 times the deflection at C, and that's times 4 inches. Plus we have the restoring moment from the torsional spring, which is the torsional spring constant times theta, which is the deflection at C over 9 inches. And all of that is divided by 9 inches. We're going to have a common delta C that comes out of these two terms. And the first term is going to give us the shock absorber spring constant K times the ratio of 4 over 9 squared, plus we have the torsional spring constant over 9 inches squared, so that's 81 inches squared. And that gives us our relationship between the force of the wheel P and the corresponding wheel deflection delta C.